Hello and welcome to the circular motion unit in Phys 1104. We're going to start by looking at some general features of circular motion, and in particular at circular motion with constant speed. This whole unit is just a special case of what we saw in the unit on motion in a plane. So a lot of it will in fact be review, but applying it to a specific sort of situation. Let's start off by establishing some terminology and also by distinguishing circular motion, which is what we're going to study, from rotational motion, which we're not going to study. So here's an example. I'm whirling a ball around my head on the end of a string, and this is an example of circular motion. In circular motion, all points in the object are tracing circles around an axis, and that axis is outside of the object. And one full turn of the object around the circle is called a revolution. On the other hand, here's an example of rotational motion. This is a turntable rotating. And in rotational motion, all points in an object trace circles. However, the axis passes through the object. So if we focus on, say, the S and the path it follows, it makes a circle. And it's around an axis which passes through the middle of the object. So this is rotational motion. And in this case, we call a full turn of the object a rotation. Now I will point out that this rotating object has two other objects sitting on it, these two masses, and they're also going in circles. And so since the axis of rotation isn't inside them, they are executing circular motion. Let's think about a merry-go-round turning with some children on it. And we can ask a very simple question. How fast is the merry-go-round turning? Well, even though that's a simple question, there are several different ways that we can ask it. So let's think about what information is needed and what we measure to answer it. And notice that this is actually a rotational motion if we're talking about the merry-go-round. But basically, the answers to those questions are going to be the same as the answers to the related question, which is how fast is this child riding the merry-go-round moving? So we've already seen the closely related terms of rotation and revolution. The time for one rotation of this merry-go-round will be the same as the time for one revolution of one of the children. And we have two ways to answer this question, whichever way we decide to phrase it. We could ask how long one revolution takes. Or we could say how many revolutions take place in a given time. The first way is called the period, the time for one revolution. And the second way is called the frequency, the number of revolutions per unit time. And these are related to something separate, which is what is the actual speed of the children, speed in the sense that we've known ever since early in the course. I'm going to time this merry-go-round to find how long one revolution of the children takes. So I'm going to watch this kid in the striped shirt to determine this. So I'm going to count 5 revolutions, and I'm going to count each time the kid in the striped shirt passes the front here. So here I go. I'll let it go around once before I start. 0, 1, 2, 3, 4, 5. So according to the stopwatch, the time for 5 revolutions was 12.435 seconds, and it's worth stopping just to talk about significant figures for a moment. Remember that my reaction time is perhaps as much as half a second. So I would expect if I redid this timing, this 4 here would change from measurement to measurement. And that means that this 3.5 is certainly garbage. These are not significant figures. So I will say that my delta t for 5 revolutions is 12.4 seconds. And now, clearly, for 1 revolution, it must just be a fifth of that, which my calculator informs me is 2.48 seconds, where again, that 8 probably has some significant uncertainty associated with it. So we found that the time for one revolution was 2.48 seconds, and that is what we call the period. Now let's find the frequency. Remember that the frequency is just how many revolutions there are per unit time. So what we know here is that there were 5 revolutions in 12.4 seconds. And if you punch that into your calculator, you'll find that's 0.403, and look at the units, revolutions per second. And that makes sense, a little less than half a revolution every second. That makes sense if each revolution takes a little over 2 seconds. So this is the thing that we call the frequency. Stand up for a moment. Get up and walk in a circle and notice 2 things. Unless you're walking rather strangely, then at every moment you are going to be facing in the direction that you are going, or in other words, in the direction that your velocity vector points. And at every moment, notice that you are facing tangent to the circle that you're walking around. So intuitively, we can conclude that your velocity, when you're in circular motion, is always tangent to the circle. Let's convince ourselves of that more formally, really just because it's a nice example of some ideas that we've been seeing ever since the beginning of the course. So think about some time interval where some object which is going around the circle starts at one point and goes to another point. Then we can draw the displacement vector, and its average velocity over that time period is just that displacement vector over the time taken. Well, let's look at a shorter time interval after the same point, and you see v_av is pointing in a slightly different direction. And if we look at a shorter time interval still, there's v_av. And if you look at the trend of which way v_av is pointing compared to this radial vector here, you can see that in the limit as we make the time very, very small, that velocity is approaching being perpendicular to the radius. And of course, this limit is what gives us the instantaneous velocity instead of an average velocity. So the instantaneous velocity is always perpendicular to a line drawn from the center of the circle to the object. We'll often talk about uniform circular motion. That means motion around a circle with constant speed. Notice the speed may be constant, but the velocity most certainly isn't. The velocity is changing direction continuously. We're also going to spend a fair bit of time looking at non-uniform circular motion with varying speed. However, most of the rest of this lecture is going to be about uniform circular motion. As you've seen earlier in the course, an object must accelerate to change its direction of motion. Well, an object that's moving in a circle is always changing direction. And so even if the speed is constant, even in uniform circular motion, the acceleration is never 0 in circular motion. And note that we've already seen that in motion at constant speed while changing direction, the acceleration points perpendicular to the velocity into the turn. Well, this is one of those things that's good to see multiple times, and let's be more precise about it. So let's think about an object moving in a circle at constant speed. And here it is at some initial time with its velocity vector pointing this way, and here it is at a later time. And let's find the average acceleration through this time interval. Well, I'll pull out the 2 velocity vectors and we'll do exactly what we've done before. I'm going to subtract, so I'll flip vi around and add it to vf, and we get our change in velocity vector this way. And so that tells us that the average acceleration through this time interval is this way. Well, now let's look at smaller and smaller time intervals, and you see that average acceleration tipping like this. And so in the limit, as delta t goes to 0, the acceleration points this way, straight towards the center, perpendicular to the velocity vector. I want to point out a word I'm just not going to use because you've probably seen it before, and I should explain why I'm not using it. So textbooks use the term centripetal when they're talking about this acceleration to the center. Centripetal just means center seeking. So we say centripetal force when we mean that the force points to the center. Centripetal acceleration means that the acceleration points to the center. Well, these terms really add little to our understanding, and they tend to confuse students, because all we mean is that these are vectors that point to the center. So be aware that these terms exist, but I'm not going to use them because we should perpetually eschew obfuscation. What do I mean? Well, perpetually means always, eschew means avoid, and obfuscation means making meaning unclear. So in other words, we should always avoid using words that are more complicated than we need. We don't need to say centripetal, it just means to the center. So let's have a quick question to check your understanding. If you're in my course, then Moodle will ask you this question before allowing you to go on to the next video lecture. If you're not in my course, I still encourage you to try and answer this question before you proceed. So here's this turntable that we saw earlier, and it's turning counterclockwise as I've drawn. And let's think about, at this instant, this mass A and the directions of its velocity and acceleration vectors. So pick the correct one.